Today we're going to be discussing net ionic equations. A net ionic equation is going to only depict the pieces of a reaction that will change states inside of that reaction. So the first thing that I'm going to do is I'm going to just go ahead and jump right into it and show you an example. It's kind of hard to theorize about net ionics. It's just much easier to show an example. So we're going to determine the net ionic equation for the following reaction. And so I have this double replacement reaction between aqueous lead 2 nitrate and aqueous sodium iodide. And I am going to be producing a precipitate of solid lead 2 iodide and aqueous sodium nitrate. Once I have my actual thing, what I'm going to do is I'm going to rewrite my equation after I break apart every aqueous compound into its constituent ions. Now, as a reminder, aqueous means that I have dissolved in water. So all of my aqueous substances are not truly like this inside of an actual solution. They are actually dissolved, which means that they have broken down and are in their individual ions. So I'm going to represent that. You just have to be careful with charges here. So lead 2 nitrate will break down into 1 lead with a positive 2 charge, 2 nitrates with a negative 1 charge. Sodium iodide would break down into 2 sodium ions with a positive 1 charge and 2 iodine ions with a negative 1 charge. The lead 2 iodide is a solid. It does not break down into its constituent ions. It is not dissolved anymore. So I will leave it as PbI2, and then I will leave that S to remind myself I didn't just forget. That's actually on purpose. And then I will also have sodium nitrate aqueous breaking down into 2 sodium positive 1 ions and 2 negative 1 nitrate ions. Once I have done this and I have all of my constituent ions, leaving it balanced, I've just taken any subscripts that multiplied in, I just put that as a coefficient now. And I'm going to go ahead and get rid of anything and everything that appears the exact same way on both sides of my equation. And them appearing the exact same way means that they are going to be in ion form on both sides of the equation. So as I look at this, I can see nitrate and nitrate both in ion forms. So that means that that's going to disappear. And I see sodium and sodium as ion forms. So those are also going to disappear. I just have to rewrite them with the ions that did not change states. They didn't go from aqueous to solid. I will just rewrite them without those, and this will be my net ionic equation. So I will have the Pb positive 2 plus 2I negative 1 going to PbI2, and that is a solid product. And again, all I did was get rid of everybody that appeared the exact same way on both sides. Anybody that I eliminated is what is called a spectator ion. This means that they didn't truly participate in the reaction, although they did hook up with somebody new. It's only because that was the only person that was left over, and they didn't form a very tight bond. They didn't precipitate out. So all of the people that I eliminated, those are my spectators, and that would be my sodium with a positive 1 charge and nitrate with a negative 1 charge. Now that I know what this actual reaction would look like on an atomic level inside of the actual solution, I'm going to go ahead and draw it out with a solution diagram. Now my solutions diagrams are just going to be a visual representation. I just need to draw my products only from my reaction. I'm going to use that same reaction that I did previously. I'm only going to deal with products because my reactants are theoretically all gone. So that means whenever I'm done and I take that snapshot after the reaction has occurred, I should not have any of the initial inputs. This initial, before we got rid of everybody, setup is what I'm going to look at when I am identifying my cation and anion and my precipitate. So my cation and anion are important because my water is polar, and if it dissolves, then that means that I am dealing with some charges being my attractive forces. So I need to identify my cation as my sodium with a positive 1 charge. Remember that cats have pos, so cations are positive. So my cation is sodium, my anion is nitrate with that negative 1 charge, and then my precipitate, my solid, was my PbI2. And that means that I will have to depict it just slightly differently. What I'm going to do then is I'm going to go ahead and draw out my diagram. I am going to be careful as I'm drawing out this diagram to make sure that I am keeping all of my counts for ions the same. So that means however many sodiums I needed for nitrate in the actual equation, that's how many I'll need in my diagram, and however many iodines I need for every lead, I will keep the same as well. Okay. When we are going to draw a diagram, we're going to go ahead and establish a legend. This will help us make sure that everybody knows exactly what's happening in our picture and make it look nice and neat. So I have all of my initial ions associated with a different shape and color to help, again, differentiate it. And then I have water here, which was not in my initial equation, but since it is the universal solvent, it will appear in my diagram. Water, I have this little Mickey Mouse looking thing, and I have my little hydrogen ears and my oxygen head, and those will come into play. So I have my actual diagram. You can see that the pieces that were still aqueous at the end, the sodium nitrate, those are going to be floating and surrounded by those water molecules. And my precipitate, which was a solid, is at the bottom. And I'm just making sure that I am maintaining the correct amount of leads versus iodides, all that kind of stuff. So you'll notice as I have my sodium and my nitrate surrounded by water that the waters are not facing the same direction for my sodium as for my nitrate, and that is for a reason. The hydrogen ears on that water molecule are actually partially positive. And since they are partially positive, they are going to be attracted and point toward anything that is negative. So my negative ion, which is that nitrate, will attract my my hydrogen ears, and so those will point toward it. And my oxygen head is partially negative, and so it will be attracted to my positive sodium. So you're going to want to have at least 3 waters around it, and then you're going to want to watch your orientation to your waters. Your ears, your partially positive hydrogens should be pointed toward any negative aqueous ions, and your negatively charged head will be pointed toward any positively charged aqueous ions. Last thing, I'm just going to go ahead and point out, I already said that my precipitate was on the bottom, but just explicitly, your precipitate should be on the bottom. You shouldn't have any waters interacting with it because it is not dissolved, and the waters interacting is just how we showed that it is dissolved. So don't have any waters interacting with it directly. Just make sure that you have the correct amount of your positive versus your negative in your final drawing.